Does anyone know what the word ionic means? Or where it's applicable? Have you heard of an ionic bond? Right? Ionic bonds and covalent bonds are two main types of chemical bonding. And so ionic bonds is when we have a trading of electrons. There is a trading of electrons. Covalent bonds is when there is a sharing of electrons. So ionic bonding is what we're going to talk about first. More specifically, ionic naming. We're not going to go too much into the bonds behind it yet. But ionic naming is between a metal and a nonmetal. So these rules that I'm going to give you for naming compounds on ionic naming, they only apply when we have a metal and a nonmetal in our compound. Okay? And more specifically, I want you to think about it in terms of a cation and an anion. Look at the periodic table. Where are the metals found? On the left side, and nonmetals are found on the right side. So another way we can explain that is in terms of a cation bonded to an anion. So where are the cations found on the periodic table? On the left side. Remember what cations, are they positive or negative? They're positive, right? We talked about that last time. An ion is any charged particle. A cation are the positively charged particle. Anions are the negatively charged particles. So cations are on the left, anions are on the right. So anytime we have a bond between something on the left and on the right, this is considered an ionic bond, an ionic molecule. And so we're going to use these rules that I give you today for naming those types. So you will have to be able to look at a compound and say, is it an ionic compound or is it a covalent compound? And then you can determine how to name it based on that fact. Okay? So, metal and a nonmetal, or cation, anion. Okay? Now that we've established what type of naming we're going to do, let's start kind of jumping into here. We're going to start developing and naming chemical formulas. Okay, so a chemical formula, it tells us the relative number of atoms in a chemical compound. The relative number of atoms in a chemical compound. And so what I mean when I say relative is that we're looking at the ratio of these. So in an ionic compound, we always are dealing with the most reduced version of a compound. Okay? So if I had a compound Na2Cl2, is that the most reduced version of that compound? No, right? Because how many sodium atoms are there in proportion to how many chlorine atoms, right? What's the ratio here? 1 to 1. So my real chemical formula should be NaCl. So when we're dealing with ionic compounds, it should be the smallest or the most reduced version. When we start looking at covalent compounds later, that will not be the case. But in ionic compounds, it should be the most reduced version of that. Okay, the most reduced version of this. Okay, that's what I mean when I say relative number. So if I have, let's see. Right, what would be the most reduced version of that compound? Good, MgCl2, right? Each of these are divisible by 2, so that's my most reduced version. That's what I mean when I say relative number, is that it tells us the ratio of chlorine atoms to magnesium atoms within a chemical compound, or sodium to chlorine, or whatever it is. Okay, the most reduced version. Okay, so I want you to either look at your periodic table of ions or your regular periodic table. If you want to get out your regular periodic table as well, you can. But this is, looks exactly the same, except it just has charges instead of atomic masses, which we don't need anyway. We need to review what valence electrons are. what valence electrons are and what's the pattern with valence electrons on our periodic tables. Okay, first of all, what are valence electrons? Good, they're the outermost electrons, which means they are available to bond. Available to bond, okay? So how many valence electrons do the group 1 elements have? 1. And how many valence electrons do the group 2 elements have? 2 and 3 and so on, okay? We skip the transition metals, right? Then we move over to group 13 and they have 3, and group 14 has 4, and group 15 has 5, and 6, and 7, and 8. Okay, right? We skip the transition metals, but that's our pattern for valence electrons. Okay, are we on the same page with that? So group 17 has how many valence electrons? 7. Good. Okay, so now let's think about this. We're going to determine how these elements are getting their charges. Where are these charges coming from? Okay, if I look at group 1, and let's say I look at lithium, right? And I'm going to draw a really simplistic model for lithium, not really even atomically correct. But let's say lithium, it has 2 shells of electrons, and in its outer shell, we know it only has 1 electron because it has 1 valence electron. Would you agree with that part? So lithium has 1 valence electron. And we say electrons want what we call the octet rule. Elements want the octet rule, which means they want a full shell of electrons. Okay? So underneath lithium's outer shell is a full shell. So is it easier for lithium to give away 1 electron or to take in 7 more? It's easier for lithium to give away its extra electron, right, to remove that outer shell and to be left with a full shell underneath than to take in 7 more. Okay, it's easier to give it away. So when lithium gives away that 1 electron, what happens to the charge of lithium? It goes from lithium neutral to lithium plus 1, right? Because it's short an electron. It gave away an electron, which means now it has more protons than electrons. Okay, that's where that plus 1 charge comes from, and that's the case for all of group 1. Right? When it's a charged particle, it is much easier to give away that outer electron than to take on 7 more. So its charge is plus 1. Okay, so when the plus 2, right, in group 2, what does it mean they've done to become that charged particle? What have they done? They've given away their 2 outer shell electrons, and they're left with a full inner shell. That's where we get that plus 2 from. Does that kind of make sense? Okay, let's move over to group like 17. Okay, move over to the halogens. Fluorine, for example. Let me use a different one. Let me use chlorine because it has an inner shell. All right, so there's chlorine's inner shell, and here's chlorine's outer shell. Chlorine's outer shell has 7 electrons. Right? That's what we know about the valence electrons of group 17. It has 7 valence electrons. So to complete itself, right, to get the octet, is it easier to give up their 7 or is it easier to take in 1 extra? Take in an extra. So if I add an electron to chlorine, what does that do to the charge of chlorine? It becomes from chlorine neutral to chlorine minus 1, right? It's got an extra electron. It's got more negative charge. That's where the chlorine charge comes from in all of those groups 17. Does that make a little bit more sense where their charge comes from? Okay, that's the general practice, right? There's extremes or exceptions to the rule as you go through, but for the most part, that's the way that an element will get its charge, right? The simplistic way an element will get its charge. Okay, any questions about that? Okay, do you see some of these transition metals in the middle that have like the line through the middle and they've got 2 options? Those are ones that have multiple charges, and it just means they are stable enough to behave with differing amounts of outer electrons. Okay, so that just means they have multiple charges, and so you'll see several of those in there that have multiple charges. Okay, you will always get this periodic table of ions, so you don't have to like memorize those or anything. But those are ones that just could take on different amounts of electrons. Right? So they're comfortable with having multiple charges. They only utilize 1 charge at a time, obviously. but they could have multiple charges. That only really applies to the transition metals. Okay, everything else is pretty, follows the rules pretty well. Okay, are we ready to start naming? We're going to start with the most simplistic kind of naming first. Again, it feels like it shouldn't even be a rule, but we're going to start with something called monatomic ions. And we're going to work our way up. So monatomic, how many atoms do you think are in this? One, right? This is a single ion, okay, or a single atom. And if you look on your periodic table, they've already done this naming for you, okay? So the rules for naming monatomic ions: cations, which are the positively charged. Do you see any difference between their name and their regular element name on your periodic table of ions? If you look on the periodic table of ions, they're just listed by the regular name. So cations get to keep their regular name. So there's nothing that even changes when you talk about sodium +1, and when you talk about regular sodium, there's no difference, right, in their name. There is a difference in their charge, right? But sodium, potassium, all of those get to keep their regular name. Anions, those are negatively charged particles. They keep the root of their name, but they end in IDE. Okay? So look on your periodic table of ions. All of these guys on the right, it's no longer fluorine or chlorine or bromine, right there. Fluoride and chloride and bromide. So when you see that IDE, that means that you're dealing with the charged version of that particle. You're not just dealing with regular neutral atoms anymore. You're dealing with the charged version of that particle. So anions end in IDE. So if I asked you to write the chemical formula for oxide, you would tell me O, -2, right? It has to include that charge because oxide is a charged particle. Okay, does that make sense? Your table writes them as 2-, right? It's exactly the same as writing -2. Okay, I was just taught to always write the minus first. Whichever way you prefer is just fine. Okay? So if I asked you to write sulfide, what would you tell me? S-2, right? S2-, right? Either way. Okay, any questions with that? So IDE means that you're dealing with the charged version. Okay? Next we have something called polyatomic ions. What do you think polyatomic ions means? Yeah, multiple atoms. Good. So polyatomic ions are ions with multiple atoms. Polyatomic ions have their own name. So we're going to use polyatomic ions and we're going to use monatomic ions to help build compounds. Okay, to help us build chemical compounds, we use both monatomic ions like oxygen, okay, or oxide, potassium, calcium, all of our elements, right, and all of our ions used to build compounds. Polyatomic ions work the same way. If you look up at this box up top, it's got a whole bunch of polyatomic ions. The blacked out ones are ones you're going to have to memorize. That's why they're blacked out, because they're the most the most used ones, right? The ones we're going to use the most are, I'm going to have you memorize. But see how, look at bromate, BrO3 -1, right? If there's a 1 there, sometimes the 1 gets left off. But those are all examples of polyatomic ions. Okay, and they have their own name. And we'll look at the naming with polyatomic ions a little bit later, but for right now you just need to kind of know what they are. They're a set of atoms or a compound that has a charge. So they're not neutral compounds. They have a charge that goes with them. Okay, so those are called polyatomic ions. An ion that has multiple atoms. Okay, so we're going to use all these different types of ions to help us build compounds. So we're going to start by learning how to name binary compounds. Sorry, my handwriting is not good. Binary compounds. How many atoms do you think are in binary compounds? 2, right? So binary compounds are composed of 2 elements, or 2 types of atoms, you could say. Won't always mean only 2 atoms itself, but it might mean 2 types of atoms. Okay? Once we start looking at these compounds, not ions anymore, compounds must have a neutral overall charge. That's really, really, really important. Must have a neutral overall charge. So when you combine these 2 things, a positively charged particle and a negatively charged particle, we have to combine them in such a way that it gives us an overall of a 0. Okay, that's what neutral means, right? We're going to come with an overall 0 charge. So, let's try some. Okay? Let's say that I wanted to... Sorry, do we have everything we need with our definition? Okay. Let's say I wanted to create a compound with magnesium and bromide. Okay, let's say that I wanted to form a compound between magnesium and bromide. So I'm going to show you basically step by step how we work through this, and then you're going to have to start kind of looking at them on your own, basically. Okay, so let's start by individual ions. Magnesium is Mg, and it has what charge? +2, right? You can start memorizing that group 2 elements have a +2 charge. Group 1 elements have a +1 charge, okay? If you look at this, I want you to take a look at the patterns here so you can start seeing this, right? +1, +2, then jump all the way over and it starts working the opposite way, okay? 18 has 0, then 17 has -1, -2, -3, plus or -4, +3, +2, +1, right? There's this pattern that you should see that kind of comes to a head at group 14, right? So we're at +1, -1, +2, -2, +3, -3, and then group 14 is where it gets a little bit crazier. Okay, so those are patterns we should start recognizing. Is that making sense? Okay, so magnesium is a +2. What is bromide's charge? Bromide is Br -1. Okay, so how can I combine these atoms in such a way that I get a neutral charge? Yeah, Nicole, what do you think? 2 bromides, right? Br -1. That gives me a total of -2. One magnesium atom gives me a total of +2, which means overall I have a 0 charge. So that's perfect. The way that I write my final product is like this. MgBr2. Right? My subscript down here tells me how many of this individual atom do I need. Okay, I only need one magnesium atom. Do I have to write the 1 there? No. If there's 1 of something, you leave that 1 off. So this is telling us in this compound I have 1 magnesium atom and 2 bromide atoms. Okay? And the way I would name this compound, right? Here's my formula for it. The name for it would just be this. Magnesium bromide. That's it. That's simple. Magnesium bromide. No prefixes, nothing to tell us how many bromide atoms. It's just magnesium bromide. That's my chemical formula and my name for that. Okay. Let's try now a combination of aluminum and oxide. Okay, the thing that you should know with ionic compounds, and you might want to write this down so you remember, is that we always put our compounds in the order on the periodic table from left to right. So the metal will always come first in our chemical formula and in our name. The non-metal will come second. Okay, so you're always going to work in order of the periodic table. Aluminum is the farthest to the left, so it goes first in our formula. Oxide is farthest to the right, so it goes second. Right, so it always goes metal, then non-metal. All right, so aluminum has what charge? +3. Oxide has a -2 charge. So we need to figure out some way to make this a neutral compound. Brogan, what do you think?
2 oxides and 1.
Okay, so if I left it there, I'd be at +3 and
I mean 3 oxides.
3 oxide. Okay, perfect.
And then 2 aluminums.
Okay, perfect. So 3 oxides and 2 aluminums. Right, so that gives me -6 and +6, which gives me an overall neutral, right? That's what I want. Perfect. So I'm going to write that formula, Al2O3, right? And are these the most reduced versions of that formula? Yes, right? I can't take this divided by this and give me 1.5, right? So I can't reduce those down anymore. They have to have the, least common multiple, right? Is that what it's called, least common multiple? Okay, between 2 and 3, right? That's 6. So that's how our charges ended up with that. Okay. So the final name for this is just aluminum oxide. Okay, I'm going to show you a little bit of a shortcut here. So you need to make sure that our charges match up. If this method's super comfortable for you, great. But I'm going to show you a little bit quicker way to do this. Aluminum is +3. Oxygen is -2. This is called the cross method, the crisscross or cross down method. I'm going to get rid of the charges, and I cross these charges down. So Al2O3. Right, this is exactly the same formula as when we canceled our charges. It works every time. Okay, it works every time. Well, I got to show you how it really works first before I give you the shortcut. Okay? You need to, if you feel comfortable using that crisscross method, then you need to go back and check. Do my charges work? And is my version the most reduced version? Okay, because I'm going to show you some exceptions here, right? It's going to work every time, but there's a couple things you have to think about after you finish that crisscross method. Okay, and so I'll show you that here in a second. Okay. Let's look now at a compound between sulfide and calcium. Sulfide and calcium. So the first thing you need to be thinking of is which of those needs to come first in my chemical formula? Calcium or sulfide? Calcium. Why does calcium need to come first in my formula? Right, it's the metal. Good. So even though I tried to trick you and write it like this, you need to make sure that you're paying attention and has to put calcium first. So I'm going to go ahead and put calcium first here. Calcium +2, sulfide -2. Right? So if I use the crisscross method, okay, I get rid of my charges, I cross them down, Ca2S2. Is that my final answer? No, so what's the problem with that? They're non-reduced. It's a 1-to-1 ratio, which means our final answer has to be CaS. Right? It's a 1-to-1 ratio. So that's the only problem with that crisscross method, is that you have to make sure that you are reducing that, if applicable, after you do that. Okay?
And does crisscross method only work with their opposing charges?
We'll always be working with opposite charges in ionic compounds. So it'll always be a cation and an anion. So yeah, that's right. Okay, whenever we need a neutral charge, this will work. If we had just done our charges method, right, if we would have just looked at our canceling charges, we would have seen a +2 and a -2, which would have told you we need one of each. So our final answer still would have come out at CaS. Okay, and the name for this molecule, can anyone give me the full name for it? What is it? Calcium sulfide. Right, pretty simple, okay? So you give me the chemical formula for lithium phosphide. Give me the chemical formula for lithium phosphide. Li what? Li3P. We agree? Yeah, perfect. Okay, that's exactly it. So we would have started with lithium plus 1. Sorry, this. And phosphide was P minus 3. Okay, cross that charge down, or you see you need 3 lithiums to cancel my negative 3 in phosphide. Li3P. Okay. Give me the name for this compound. Give me the written name. So when I ask for name, I want the word form, right? All right, so 3 of them. The first and the third, you're giving me the formula. The second one, you're giving me the name. Can somebody raise their hand and give me the first chemical formula for gallium oxide? Yeah, Katie, what do you think? Ga2O3. Raise your hand if that's what you had. Perfect. Ga2O3. Gallium is a +3. Oxide is -2. So if we cross the charges down, right, that gives us Ga2O3. Okay, or if we went through the charges process, we would have needed 2 of those +3 charges, which gives us a +6. 3 of our -2 charges, which gives us -6. That's our final answer. CASE. Yeah, Brogan, what'd you have?
Calcium cyanide.
Calcium selenide. Perfect. Right, easy enough writing the name, right? Last one, beryllium arsenide. Ann, what'd you have? Be3As2. Agreed, right? Everyone have that same thing? Perfect. Okay, what questions do we have about ionic naming so far? Okay.